Good afternoon and welcome to this OASIS webinar, The Socially Useful Engineer. My name is Andrew Eckert and I am one of the business development managers at OASIS. Okay, so as always, today we have a great session planned for you, which will be delivered to you by our presenters, David de Koning, Head of Structural Products, and Angela Hu, Senior Product Manager. Now, some of you are already familiar with OASIS, but for those who are not, OASIS stands for OVE Arup Systems, and we are Arup's in-house software developer. We provide digital solutions for structural and geotechnical engineering, as well as for pedestrian simulation. Being a part of Arup as an independent company gives us the ability to focus solely on delivering leading engineering solutions. Now, some general notes before we dive in. We will have a Q&A session at the end of the webinar, and any questions you might have, please add these into the Q&A section of Teams, which you can find towards the top right-hand corner of your screen. Now, if you don't have a Q&A button on your Teams, then please just put your questions straight into the chat and we'll move them over to Q&A internally. So, without any further delay, I'm going to pass over now to David, who can begin today's session. David.
Brilliant. Thank you, Andrew, and thank you everyone for joining us. We hope that you find today's presentation informative and interesting and maybe even helpful. So I'm going to start this all by taking a little bit of a look into the past and some things that some famous engineers have said or things that have been said about famous engineers. So here we have Brunel, who, discussing one of his famous structures, Paddington Station in London, said that he designed it after his own fancy. So the social impact that he had and the way he was thinking about social impact from his engineering work was, this is what I think would be a great idea. Another engineer had a slightly different perspective on it, was Fazlur Khan, famous for the bundled tube, for developing the bundled tube structural system in the Sears, now called Willis Tower. Talked about his motivation for searching for new structural systems and how it was really the social and visual impact of these buildings. And so he didn't have any kind of distinction between, on the one hand, social impact of his work and the engineering design and the hardcore engineering that he was doing. These were tightly linked in his way of thinking. And the Brooklyn Bridge, one of the most famous bridges in the world, designed by, well-known, the Roebling family. And here we have someone saying that Emily Roebling's name will be inseparably associated not with engineering, right, but with all that is admirable in human nature and all that is wonderful in the constructive world of art. And so when we look at an engineering project, when it's done and the work that we're done and the impact we have on the world, they're not just engineering projects, they're just human projects. And so how do we as engineers come in and make a difference in this world? How do we think about it and how do we maximize that? So that's sort of the question we want to look at today. And so let's dive in. So I'm going to start by looking at three perspectives on engineering. And for some projects, sometimes you can look at a project on the left-hand side. We have the Copenhagen Metro. Metros are very useful. They help people get around. They help people get around sustainably. They help dense urban centers function and have life and allow for human contact. And we also do finite element analysis. So it's just numbers on a mesh. And these tell us, as engineers, they tell us things, but sometimes the connection between can be a bit tenuous. So when we think about social impact, right, that's one way to look at the engineering work we do. What is the social impact that we have? And the way we talk about these is very much about words like transformation and crucial to the recovery from things. And we also have, this is for a project here in Canada, talking about a new train network, talking about being closer and faster and together. This is the Line project in Saudi Arabia, talking about the sustainability of it. We have as well the Paris Olympics, Olympic Games also have these are huge engineering projects, as well as social projects, and there's always a huge discourse around the social impact. discussing some expansion of Changi Airport in Singapore, talks about maintaining or securing Singapore's air hub status. And so status is a social value. All these very different social values. And finally, again, I'm calling in from Montreal today, and this is a terminal expansion happening in Montreal. And when we think about container terminals, we don't necessarily think about harmony with the community, but that is how this project is being pitched. And it's one of the important things to address the social impact. And so social impact is very fuzzy. It's not something that lends itself to precise analysis. We don't have strong agreement in society on what's important to society, and we never have. And so this is a perspective on our projects, right? And if we want to make a big difference, we need to recognize this perspective. If we go to the other end of the spectrum, we get to very familiar engineering territory, the analysis-centric perspective. So we have analysis, and before analysis, everything before analysis is pre-processing, and everything after analysis is post-processing. This is a very precise way of thinking. It leverages, all the analyses that have been developed through the history of the engineering profession, all the scientific knowledge that we've built up, and it's, in a sense, what sets us apart as engineers from folks who merely have opinions. We can do analysis, and we have ways of predicting behavior of things. But when we look at these two perspectives, they really seem to be quite far apart. On the one hand, we've got analysis, which is a very precise mathematical way of looking at something. And on the other hand, we've got this fuzzy, almost marketing-ish view of the world, and if you talk about the same bridge or the same project as an engineer giving analytical results about that project, and then you go to the community consultation where they're explicitly trying to express the social impact, it's almost as if we're speaking different languages. And what can we do to join these together? And so what I'm going to suggest today, what we're suggesting today, and we're going to talk through some of the implications of this, is that having a design perspective, having an explicit and formal design perspective on the work we do helps us bridge this gap. And what do I mean by a design perspective? There's many ways to talk about design, and everyone you talk to is going to have a slightly different view of design. So one way to look at it, and there's variations on this, is that we start by imagining a future, right? Maybe it's a sketch, maybe it's a BIM model, maybe it's an analysis model. And so we imagine that future, and then we go and we simulate that behavior. And once we've simulated that behavior, we assess its behavior. Okay, so now we've got an option, we've got some assessment of its behavior. And we don't typically, in a project, only simulate one behavior. We have multiple behaviors. As structural engineers, we simulate behavior when the wind blows. We simulate behavior when an earthquake happens. We simulate behavior under all kinds of loading conditions. And we also have our colleagues in the mechanical space, in the electrical space, in the fire safety space, carrying out their own simulations. And when we have all these results, we can come back and we can evaluate the impact of that particular option that we've looked at. And so if we think formally about design, right, and it's not about controlling the design process, just about thinking clearly, we think about a good design process has clear definition of options. And clear definition of options allows us to clearly compare the options. And of course, to bridge the gap between those two, we have clear scope for all our analyses. So by having those clear options, we can say, okay, we're going to go from, we want to have some kind of fuzzy social impact. Well, what if we did this? And then that allows us to say, okay, well, we're looking at one particular thing, and that allows us to go off into the world of analysis with the precision we need to carry out a useful analysis. And then we can come back and feed that in to a social impact assessment. And so we have these three perspectives. The analysis perspective, which has the high liability, it has to be right, has to be precise. The social impact, which is the ultimate value, and it's what your family understands at the dinner table. And in between, we have this design process that is sometimes organized, sometimes not, sometimes informal, sometimes formal, sometimes clear, sometimes confused. But if we can think clearly about these, then that can allow us to have a bridge between these two. So having said all that, I'm going to hand things over to my colleague Angela, who is going to give some more specific examples of how some of the tools that we develop can be used if we're thinking about design, and then I'll come back and wrap things up.
Yeah, thank you, David. So I'll be talking a little bit about the thinking and the types of tools that help put design at the center. And so if we're thinking about a design-centric type of workflow, what is most important at the heart of everything are the iterations. And what we mean by that is that is how the design progresses over time and how you communicate during the various stages what the social impacts and what are the trade-offs between each design. And in order to carry out these iterations effectively, some of the most important things we need to be able to do is, one, to zoom out, to be able to compare the different options and how they relate to each other and what the trade-offs. And secondly, to zoom in on, so basically taking a lot of options and then comparing them against an objective to select one that might be better than some of the others. And then secondly, it's about zooming in on details to create new options. And that more or less summarizes both the convergent and divergent phases of design, where you use one iteration to narrow down an option and then use more information from that better option to create even more options and progress that design process. And so if we look in on the very first one, in terms of zooming out to compare options, some of the key things that we end up thinking about is, well, how do you quickly extract the key outputs? How do we evaluate these options with confidence and with enough speed so that we can look at a lot more options? And so one of these tools that we have that is really helpful for this is our GSA Grasshopper plugin. So this is a parametric plugin for Grasshopper and allows you to do finite element analysis all within the environment of Rhino and Grasshopper. So what this means is that you can actually define your entire analysis model in a very parametric way, play around with the toggles, see the impacts to the structure, and very quickly evaluate a lot of different options and show that impact in terms of the images to the end client. Another way that we can look at it in terms of helping that design iteration process is about, well, how can we make it faster to get to that next iteration? And one of the ways that we could do that is finding tools that state the objective of something as opposed to looking at some of these options, eliminating the need to do comparisons on every single small little detail and looking more at the holistic things. So for example, one of the things that you might need to do is to run a modal analysis. And a question often comes up is how many modes is the most optimal amount? And one way that we can do this is instead of guessing and testing with each time you run this, you can actually say, okay, well, I know what my objective is. I want to meet 90% mass participation ratio. So you can run an analysis to then just state that this is my objective and the analysis will automatically meet it. And what that allows you to do is to be able to focus your attention on some of the more important questions of, how many beams, what are the column spacings, as opposed to finding the best way analysis to actually carry out what you need to be able to do. And so that is talking about how to zoom out and compare options. Something that I also want to talk about is the importance of zooming in to create new options. And the most important thing along this process is that the more information you have about something, the better your guesses are. And so what we often do in order to help with speed is to, when you evaluate a design option, to put it through a process that takes care of a lot of the detailed calculations. And in the end, you get that one key result that you're looking for. And that's really helpful when we were in the first phase about comparing options. But once you find one thing that works better than the others, you almost want to go on to the next step and figure out, hey, can we go along those lines to make it even better? And what you can do is that if you take that black box that is the processes that we were trying to hide earlier, and you open that up, what you find inside of there are clues to help you identify how to improve the design. And so for the next little bit, I'll be talking about a couple of examples of some tools that we have within our software that help you uncover some of those clues and aid with that design process. So one of the first things that we have is in GSA is the concept of design layer and analysis layer. So the design layer is a layer where you do your modeling, where you make changes and you apply loads to the structure. But what we also have is a representation of that same geometry, but in the analysis layer, which is the actual finite elements. And having that is really useful because it allows you to see what exactly is being connected, what is actually being used in a solver, for example, to calculate the forces, allowing you to better understand your structure. And so something that you might be doing in the design layer is, let's say, apply loads to a bunch of the entire wall, let's say. But something that you can tweak in the analysis layer is add a little bit extra load to see in one area to see how that impacts the structure. And so the power of this is that it allows you to really zoom in on the details of that finite element analysis, truly understand it, while also still being able to model structures with speed. So how can that be useful? Well, let's give an example of a footfall analysis. So a footfall analysis is done to carry out to see the impact of floor vibrations under particular foot loading. And so this is one of the outputs from it. It's called a response factor. And all you need to really know about it is that the larger that number, the more floor vibrations can be felt. And as you can see in the sample slab here, there's one area that's particularly bad, and you want to be able to find a way to control that. So you have options, right? You have options about, do you add more beams? Do you add more mass? Do you change the amount of the frequency of footfalls to see if you can limit that? There's a lot of different options you could choose here. But when you dig into the behavior of something, you can know more about it to know which option might be a better option. And so if you look into here and dig into the analysis layer and you look at the response of the worst node here, what you can see here is plotted on the vertical axis, the response factor. So what I was talking to you about earlier about the bigger the number, the higher the amount of vibration that can be felt. And then on the x-axis, it is the walking frequency. And as you can see over here, in this case, it's actually really easy to push that response factor down if you reduce the walking frequency. And this is one way where you can check to see what you can do. Alternatively, if you take, this is just from a different model, but sometimes the graph looks a little bit more like this. And if you're looking at something like that, you could say, actually, walking frequency, if you reduce it by a little bit, it actually wouldn't make a really big impact because you're just going from here to here and the maximum is over here. And so what getting these detailed insights allow you to do is really be able to narrow down your range of options and know where to put the effort into for your next iteration. Something else that we might come across often is related to getting analysis error messages. You put together your model, you're about to look at your option, you hit run, and you see, oh, wait, it's not running because there's a warning. And oftentimes what that leads to is a lot of investigation on what you might need to change for this. And so something that we have in our software is called model stability analysis. And what this allows you to do is to be able to examine the structure and get a plot of where it thinks your instabilities are coming from so that you can further look into that specific area of concern, identify the problem, fix it, and move on to your next iteration. And finally, something that I'm pretty excited about is something that we are working on that's coming up next, and that is the integration of Compost, our composite steel designer, with GSA, our overall global model analysis. And what this will allow you to do is to be able to model the entire structure inside of GSA while still being able to design each individual composite member inside Compost, and they will be tied together so that you will have information from both of those to help make your decisions. You could take a look at the overall global deflections combined with the deflections that due to the composite action, in addition to looking at the design of the beam itself, the penetrations, things like that. And together, when you have both of this information available, will make it easier to make future decisions. And so with that, I will pass it back to David.
Thanks, Angela. All right. So a lot of what we're talking about today is this going back and forth between that higher level, what's the impact, how do I explain this, and then diving back down into that engineering analysis and that detail. At the end of the day, a structural engineer is someone who takes responsibility for the safety and performance of a building to society. And that is a real challenge sometimes. So this is very often how we feel, especially today. So we have structural engineers working away, and there's automated design coming. And what does that mean for my work? What does that mean for my responsibility? You've got tight deadlines because clients have realized, hey, can't you automate this? This should be faster. And of course, over the past couple of years, there's been the specter of generative AI. And so there are some tools out there and some ways of thinking that say, okay, well, maybe we won't need structural engineers anymore because the computer can just do it all for us. I can just generate a building, and that will be the case. And how do we as structural engineers respond to that? And again, this idea of being very clear around the design process and how that fits into things is a key in our thinking to go forward. So control comes from clarity, and clarity of the connection between social impact and the analysis we do. If we have control over that and we have clarity over that process, then there'll be a role for structural engineering. And so the first thing to remember is that analysis is what sets an engineer apart from someone who just has an opinion, right? Precise predictions of behavior and a comprehensive understanding of safety. The need for safety and the need to understand behavior of things before we build them, that's not going anywhere. On the other hand, we don't, as engineers, just want to execute someone else's vision of the future. We want to get involved in shaping it, right? That technical understanding of how the world works, of physics, informing that is how we get cost-effective and beautiful things. And so sitting in between, we want to have design clarity, an organized and rigorous and a flexible and responsive design process. And there's a lot we can do just by having clear thinking. Am I analyzing just one option today, or am I looking at this? Okay, how does this option feed back into the design process? When you have a clear understanding of the design process and how that fits, you create space for rigorous analysis, right? And you create a channel for the outcome from that analysis to influence the world that we live in and the projects that we're working on. And in addition to this being a way of thinking, you can also come and demand that from your tools. So we need to have the right tools, obviously, for the right job. So there's analysis tools and there's design tools. And very often, there's a couple of pitfalls, or a couple of things to be aware of. Is very often in our industry, and this is the case for some of our tools as well, they've grown up from analysis tools and they've got some design features added into them. And so it's important to think about that. But an analysis tool, if something is an analysis tool, it needs to be precise and detailed. It needs to be flexible. It needs to be transparent, right? We need to be able to check this, because at the end of the day, as a structural engineer, you take responsibility for the work. And so that means whatever the software spits out at you from that analysis, we need to be able to take responsibility for that. On a design tool, we want to be able to rapidly express different options, right? We want to have clear bookkeeping. What are the options we considered, right? How many times have you been toward the end of a project and someone says, hey, could we do this with different structural system? And then it's a scramble through the notes from the beginning of the process of, yeah, we did look at that at the scheme design, and we, what was all that? So a strong design tool is one that will help you keep track of what you've considered and why the decisions were made. And of course, it has to help us communicate, right? A design tool that helps us communicate these things. And these tools feed to each other. So an analysis tool, analysis provides feedback into the design process, and the design process shapes and provides a framework for deep dives into the analysis. So there's this back and forth. So we look at things from whatever tools you're using, even if it's an early scheme design where everything's not computerized. Thinking about this can look really good. And then also when you're looking at tools and evaluating tools, this is a framework for saying, okay, is this helping me just with analysis, or is this helping me with design, or just with design? And so there's a very timely question from Sam here saying how this affects our roadmap. And so I'm just going to tease a cloud integration that we're hoping to release in the next calendar year. If you're curious about this, please reach out to Andrew or Angela or myself. This is a cloud integration where we can keep track of revisions of your analysis models, of your GSA models, and extract key results. And so this is in the first version, we're looking at footfall analyses, looking at how that changes. And we know that in the world of BIM, there's a lot of version tracking and progress tracking. What we're trying to provide is something here that really is for engineers, looking at engineering analyses, being able to quickly side by side look at these things, look at the key results, and this is a really important thing for us. And so if you are curious about that, if you're curious about being an early adopter customer, we would love to chat with you about that. To end, I'll end with a quote from another engineer, Ove Arup, talks about engineering problems being underdefined and that there are many good, bad, and indifferent solutions. We could also just say that social problems are underdefined, and we can say that social problems and engineering problems are ultimately the same thing. An engineering problem is a social problem, and a social problem can benefit from engineers' input. And so thinking about the analysis and the design and the social impact, these three different perspectives on our work, thinking clearly about those and demanding that our tools support us for that is one way that can help us as we go into the future through change and continue to shape the world around us and bring all of the knowledge from the engineering profession to make our cities and our countries better. So with that, I hope that this has been thought-provoking, and if there's any questions either about anything that you've seen or any reflections on that, please feel free to drop them into the Q&A or into the chat.
Okay, thank you very much for the webinar, David and Angela. I'm going to have a look now and see what questions we have. Right, first question is, what does the roadmap look like for design and analysis within GSA? What can we expect to see next?
So, I'll elaborate a little bit on that. We was teasing this cloud integration we have upcoming, but the roadmap for us has two very distinct sides, right? One is we want to help support that design process. We want to provide these tools that track those things, but transparency of our tools is incredibly important. So we're looking at, obviously we have, as Angela mentioned, the design layer, which is very similar to what all our competitors have on the market, but we have this explicit and editable analysis layer. And so keeping that going strong is very important. Keeping the two aspects of those available, transparent, and checkable is very important. Another thing we're looking at is on top of our cloud integration, hoping to provide really comprehensive reporting and create reports that can pull in data from multiple analyses, and really just provide a really great platform for communicating the impact of these various options. So these are the sorts of things that we're looking at. And in the short term, the two big features to look for is going to be integration of composite design with the overall analysis model, and not just generating the individual member files, but bringing the composite stiffness back into the global model, and also this cloud integration.
Great, thank you, David. Another question, does GSA work with BIM platforms such as Revit and vice versa?
Absolutely. We have a number of ways to interact with Revit. We have a Revit plugin that allows you to push to GSA and to pull back to bidirectional Revit plugin. Angela also showcased our GSA Grasshopper plugin. And so whether there's a number of workflows, you can start from Revit as your authoring platform and push out to GSA. We've also started to see a number of teams start with a parametric design and generate side by side from the same inputs an analysis model and a BIM model. So rather than going from BIM to analysis, you go from parametric inputs and you generate synchronized models. And the Grasshopper platform is very powerful for that. And finally, all of our products have APIs, and they're automatable with in Python and C#, in Grasshopper, obviously. And we know a lot of BIM tooling and BIM workflows are coming with automation there, and we integrate very nicely with that.
Okay, next question just come through. Looks like someone's having difficulty with meshing on an existing software. How does the GSA meshing work, and how would you compare it to other methods?
So we overhauled our meshing 2 or 3 years ago. So anyone who's had experience with GSA meshing 5 or 6 years ago, strongly encourage you to come have a look. We have best-in-class meshing, and the way it works is in our design layer, you draw members, you draw beams, you draw whole slabs, you draw your columns. By default, whenever these touch each other, the meshes are you're gonna get a consistent mesh. So we start by solving all the intersections, and then we mesh each of these elements. Every element, you can set the mesh density separately from what you want. So if your walls, for instance, you want to have a 0.5 meter mesh density, and your slabs, you want to have a 2 meter mesh density. Well, what's going to happen is when you generate the analysis model, and in fact, before you generate it, you'll get an instant preview of what that mesh will look like. But when you generate that analysis model, you will end up with a very tight mesh on your wall. And instead of having a 2 meter mesh everywhere with then joints to join them, what you're going to get in your slab is a transition. The slab around the column, around the wall, is going to have a very tight 0.5 meter mesh, and then grow out to the overall one. So we have very strong meshing, especially for if you want to have an actual consistent mesh as opposed to disjoint meshes with then rigid constraints to tie them together to sort of zipper them up where they come together. And again, I know some of GSA has been around since the 80s. So if you haven't looked at GSA's meshing in the past 3 or 4 years, absolutely worth a new look. And as an aside, we know that a lot of structural engineers like to mesh in their parametric software in Rhino, and Rhino's built-in meshing builds visualization meshes, builds triangles that are badly shaped, not at all appropriate for finite elements. So you can use the GSA Grasshopper plugins to generate a beautiful finite element mesh within Rhino and Grasshopper, and bring that in. And we do have some people who use GSA just for the meshing, and then bring it off to things like LS-DYNA and more advanced nonlinear solvers. So absolutely, the meshing is beautiful.
Okay, great. Another question. What are the plans for CLT and timber structures? Is GSA, are we able to do that as we go along? In the future,
yes.
or at the moment?
So at the moment, you can model a CLT in GSA, and the reason you can do that is because GSA is so flexible and it leaves it out there. That being said, it's not a beautiful and really easy process right at the moment. You've got to calculate equivalent stiffnesses yourself. We are currently researching how we're going to do that and bring that out. It is on the roadmap to be able to define CLT panels and get that effective stiffness, and the idea being that be able to draw each of your CLT members, control the meshing, and get the appropriate stiffness for that. Yeah.
Right. Okay. If you are designing or analyzing, in fact, with GSA and Grasshopper together, if you want to save the model, does that have to be? Can that just be saved within GSA? And can a third person then open it in GSA without Grasshopper?
Absolutely. I mean, this gets to the nub of adoption of these fancy parametric workflows. And so first, I would recommend, and maybe we can drop a link into the chat, having a look at our last webinar that we gave, where we talked about the generation gap. And we spoke explicitly about this. And so to summarize, or to answer the question, instead of just prevaricating, when you run GSA inside Grasshopper, you are running the GSA program inside Grasshopper. There is a save as component, and it saves a GSA file. There is an open component, so you can open a GSA file. So you can have a parametric workflow that either takes an existing analysis model, opens it, and run some analyses, make some modifications. Or you can have a parametric workflow that just generates one. And so if half your team is really comfortable, or let's give a very typical example, right? Junior engineers, younger engineers building a beautiful parametric model, very comfortable with that. Senior engineer, very comfortable with a desktop application, looking at a particular model, and they're the ones who've got to do the checking. With GSA in Grasshopper, this is a seamless workflow. You go save as, and you take that, you open it in GSA, exact same model, everything's there. And that's, we recognize that not everyone has the same level of comfort with parametric approaches, and it's really important to be able to gradually adopt them and to be able to use them side by side with your traditional, I have opened a file in my desktop application and I am going to poke at it. Yeah.
Great. Okay. That brings us to the end of our Q&A sessions, unless anybody has any final questions they'd like to put forward. If you do think of further questions in the future, please email us at oasis@arup.com. You can also use that email address to request a trial of GSA if you would like to try any of the things that you have seen here today. We look forward to hearing from you. And for now, that brings us to the end of our webinar today, and we will wrap up our session. Thank you, everybody, for joining.
Thank you all.
Thank you all.